All right, so let's move on to section 25.5, which deals with sequencing a peptide, or basically determining the order of amino acids in a peptide. And one of the ways we can do that is using a technique called the Edmond degradation. And the Edmond degradation is a two-step process. It involves removing one amino acid from the N terminus of a peptide as a phenylthiohydantoin. How's that? Phenylthiohydantoin, or a PTH derivative. And the PTH derivative is used then to identify the amino acid. So let's say you have a peptide. In this case, you can see that they put the N terminus on the right-hand side, and that's for instructional purposes. So you have your peptide, and you just remove one specific amino acid that's on the N terminus, and you react it with this molecule here. So this is called phenyl isothiocyanate. And then you treat it with this one here. This is called TFA, or trifluoroacetic acid. And then you end up losing that amino acid. And then it gets incorporated, your R group gets incorporated into your phenylthiohydantoin derivative. And then you just analyze that. So it's this molecule here that gets analyzed by mass spec. And then each of them has a unique profile. There's only 20 amino acids, so that way they can do it very quickly. And so the process, it turns out the process can be automated, and you can analyze peptides that have up to 50 amino acids total in the peptide chain. I'm not going to ask you this mechanism, so I'll write it in here for you. Will not ask. But the bottom line is basically the amino group reacts with the phenylthiohydantoin, and then it does this nucleophilic attack and a couple of proton transfers. And you see that not even the entire mechanism is put in here. So I won't ask you to do that. You just have to know that the phenylthiohydantoin derivative is the one that gets analyzed by mass spectroscopy, or mass spectrometry, and then you're able to determine what the structure of this amino acid residue was on your chain. Anyhow, so besides the Edmond degradation, let's say you have a big peptide, because I just told you that the Edmond degradation only works for amino acids that are up to 50, or sorry, peptides that are up to 50 amino acids in length. So what if you have a big old peptide, something that's got 100 of amino acids, or maybe more? Well, in that case, you're going to take advantage of an enzyme called a peptidase. And there are many peptidases out there. There's only two of them that we look at in this class. But what a peptidase does is, if you've studied biology and you know what an enzyme is, you know that a lot of them end in A's. And then a peptidase, what it does is it's going to hydrolyze a peptide bond, okay? But the thing is that a given peptidase is going to hydrolyze specific peptide bonds. So the first one that we look at is called trypsin. And we also look at chymotrypsin. That's on the next slide. So trypsin cleaves the peptide bond at the C terminus side of arginine and lysine. And what do you notice about arginine and lysine? Both of them are basic, okay? It doesn't include histidine. It's not in there. But remember that for each one of these amino acids, the order goes N-C carbonyl. So that's why it cleaves on the end, on the right-hand side of the lysine. And then the same thing for the arginine. Again, it goes N-C carbonyl. And so it hydrolyzes on the right-hand side. So then you go over and you look at the new fragments, okay, after you treated your peptide with trypsin, and you can say, well, the end of this one is a lysine, the end of this one is an arginine. The end of this one is not a lysine or an arginine. Therefore, this must be the C terminus. C terminus, right? And you kind of go like that. But if you're saying, well, then how would I know which one of these to put, before the serine here? It's a good question. And you wouldn't, but you take the same peptide, like this one here, you take the exact same peptide and you treat it with a different enzyme. Okay, so you treat it with something like chymotrypsin. And what chymotrypsin does is it cleaves at the carboxyl end of aromatic amino acids. So what are some aromatic amino acids? Phenylalanine, tyrosine, tryptophan. And so again, it's the carboxyl end, or the C terminus end, okay? Not C terminus end, we'll just leave it as carboxyl end. So we have N-C carbonyl, so it cleaves on the right-hand side of the phenylalanine, tyrosine, and tryptophan. So then, and this is the exact same peptide that was on this slide here. So now we can look at these new fragments, all the fragments here, okay, these four fragments, and we can say, okay, phenylalanine, tyrosine, tryptophan. Oh, This one is not one of those three. Therefore, this must be the C terminus. And if you look at what I wrote in the previous slide, I said the histidine was the C terminus, right? So just to give you an idea, you look at this one here, it goes histidine, leucine. So it goes histidine, leucine, tryptophan, serine going backwards. So we go histidine, leucine, tryptophan, serine, and then we know that arginine and glycine must be the residues that come before it. And then we just keep backtracking with all those fragments until we figure out the structure of the entire peptide. So let's say you had the question like this one. This amino acid has, or this peptide has 22 amino acid residues in it. By the way, if you didn't understand the word residue, it just means when you have a bunch of amino acids linked together. If you're talking about one individual one, we call it a residue sometimes, okay? So you've got 22 amino acid residues together. First, you treat it with trypsin. Then you treat it with chymotrypsin. Okay, and then you get different fragments. Well, trypsin is going to hydrolyze on the carboxyl side of arginine and lysine. So we have arginine, lysine, arginine. Oh, look, here we have valine. Okay, so we know that this must be the C terminus. Let's look at the chymotrypsin. Chymotrypsin cleaves on the carboxyl side of tryptophan, tyrosine, and phenylalanine. So they are all in these ones. But look at this. Now we have a valine. Okay, so that tells us for sure that the valine is our C terminus. So we know for 100% with 100% certainty that the valine is our C terminus. And then what we're going to do is we're going to take the residues or the fragments from both of these, and we're going to go backwards. Okay. So since the valine is the C terminus, I'm going to start down here in the bottom right-hand corner, and I'm going to say valine, okay? And that is going to be appended to a alanine. So then I've got my alanine here, okay? So I can cross these two off, and now I'm all the way here. So now I have phenylalanine, proline, glycine. So let's do those. So we have phenylalanine, then we have a proline, then we have a glycine, glycine, like that. All right, so now I've gone up to here. So now over here, I'm going to look for phenylalanine, proline, glycine, and I see them right here. It's the only place I see those. So I can cross those off, and I can say, okay, the next one must be arginine, cysteine, and methionine. So I'm going to put those in. So we're going to say arginine, then cysteine, then methionine. So I can cross all these off. I look for those three over here. I see arginine, cysteine, methionine right here. So then I know it must be phenylalanine next, right? And I'm looking right here, phenylalanine, histidine, tryptophan. So phenylalanine, histidine, okay, and I'm going to go back like this, okay? And then here it's going to be tryptophan. So I've got these ones done. So I come over here, I look for phenylalanine, histidine. So those are here. Then I have tryptophan. This is the only tryptophan in the whole thing. Over here is this tryptophan. So I know before the tryptophan, it must be arginine, leucine, isoleucine, valine, proline, lysine. So I can put all of those. There's 6 of them. Oops. So I have my tryptophan. Then I have arginine. Just bear with me. There's 6 of them here. Arginine, and then leucine. My spheres are getting more oval shaped as I move along here. Then isoleucine, then valine, so valine, then proline, and then lysine. So lysine, like that. So I can cross all those off. So I look for, let's see here. So I've got arginine, leucine, isoleucine, valine, proline. Then I have lysine here. This is the only lysine in the entire thing. So I know that after that, it must be tyrosine, alanine, valine, phenylalanine, methionine. And then I'll be able to cross these ones off as well. So then I have lysine, then I have tyrosine, then I have alanine, Then I have valine. I'll go back up here. Then I have, so I've done these ones, and now I have phenylalanine and methionine. So phenylalanine and methionine. And yeah, there we go. So if I count those up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Boom, there we go. So that is how you use the fragments from trypsin and chymotrypsin to put together the structure of this peptide. Give me a thumbs up if you follow me on the rationale. Not mega complicated or anything. It's more about keeping track of them, okay? And it's just sometimes if you're doing these, if it's got more amino acids, you might lose track. So you got to kind of make sure to cross them off as you go along. All right, so that covers sequencing of a peptide. So again, just to review, we learned two ways to do it. One way is the Edmond degradation, where you make the phenylthiohydantoin derivative. The only problem with Edmond degradation is that it only works for small peptides, so fewer than 50 amino acids. Once you get into big ones, then you're going to want to use enzymatic cleavage and then just analyze the smaller pieces. And then you can sequence it. You can go backwards like I did here and put the whole thing together. But what if you want to make a peptide? And the first company I actually worked for, I worked next to a guy who was an expert in peptide synthesis and learned a little bit along the way. Not nearly as much as what he knew, but I learned a couple of things. And I made a lot of peptide bonds along the way too. So it says here, to form a peptide bond, all it involves is a reaction with the N terminus of one molecule with the C terminus of another molecule. Okay, and obviously you can see here, you must lose water. Maybe not as a water molecule, but you lose this hydrogen and an oxygen, and you lose a hydrogen here, right? So together that makes a total of H2O, anyhow, which is lost. Now, how do you put these two together? Question mark. Well, it says here one popular coupling agent is used for this purpose. It's called DCC. Try this on for size. Dicyclohexylcarbodiimide. Oh boy, that's a long one to remember. But DCC is a really great coupling agent. It's just a white solid. It has to be stored in the freezer, but that's no big deal. Anyhow, and there's a new functional group for you, a carbodiimide. Now, I'm not going to ask you the mechanism of DCC coupling, but that is one of the ways that you could put these two together is to use DCC, dicyclohexylcarbodiimide. So take a look. The mechanism here, I'm just going to write will not ask, okay? And you can see that not even the whole thing is put here. They just put proton transfers in here. So all you have to know is if you're putting a carboxyl and an amino group together to make an amide or a peptide bond, you're going to use DCC. Now, let's think about it in a practical manner. Let's say you have two different amino acids. You've got this one with the blue R group, and you've got this one with the red R group. If you just put these two amino acids in some kind of flask, okay, there's a flask, okay, and then you just start stirring them around and you put in some DCC, there's a mixture of 4 possible dipeptides that you could get, right? The C terminus of R1 could react with the N terminus of R2. The C terminus of R2 could react with the N terminus of R1. 2 R2s could react, 2 R1s could react, and so we get a mixture of 4 different compounds. Not very useful. Okay, this would be kind of a useless reaction. That sounds miserable. And so what we need to do, let's say we just want to make the coupling between this carboxyl group and this amino group. Well, in that case, we need to mask the functionality of this amino group, and we need to mask the functionality of the carboxyl group, right? So how are we going to do that? We're going to use a protecting group. And you remember for protecting groups from way back when we talked about hydroxyl groups being protected as trimethylsilyl ethers to prevent any side reactions in Grignard chemistry. So we're going to look at ways to protect the N terminus or an amino group and ways to protect the carboxyl group as well. So if you could have those two groups protected, then you could selectively react the two groups that you want, make the peptide bond that you want, and then just remove the protecting groups, and there you go, you're done. So it takes a little more chemistry, but you only end up with 1 product instead of 4. So that sounds pretty darn great to me. I don't mind doing a little extra work if I can limit the number of side products that I get. So how would you protect the amino group? Well, this is brand new. And the way you're going to do that is you're going to protect it as what's called a carbamate, okay? So a carbamate is this here. So let me just write up the structure of a carbamate. So it would look like this. So if we have something that looks like this, okay? So this is the structure of a carbamate. So you can see the N terminus, okay, or the amino group, whatever you want to call it, reacts with this molecule here. And this is called diterbutyl dicarbonate. So I'll put the name down here. This is diterbutyl dicarbonate, okay? We just call it BOC, okay, for butoxycarbonyl. We just call it BOC anhydride sometimes, or sometimes we'll just say BOC 2O. Okay, either one is fine. And then sometimes you'll see people call it TBOC 2O, like that, just because it's tert-butyl. Either one is acceptable. I will not ask you this mechanism. Will not ask mechanism. Okay, but there you go. So you add the BOC group onto your amine using BOC anhydride, or what we call diterbutyl dicarbonate. So let's take a look here. So you take your amino group. To make the carbamate, you treat it with BOC anhydride or diterbutyl dicarbonate. On the previous slide, I just wrote BOC 2O like this. I guess it's more correct to put the BOC, the BOC in brackets, but either way is same thing. People do it either way. And then you have your BOC protecting group. So you notice you have your carbamate here, right? Okay, so now that we figured out how to protect the amino group with your BOC group, which is pretty straightforward, okay? The installation, I'm going to put here, again, will not ask. So don't worry about it. What you need to know is this. You need to know that if you take your amino group and you put it with BOC2O, you end up installing the BOC group. So instead of writing this whole thing out, you can even write the condensed structure out. You could just say NHBOC and then BOC, not Blue Oyster Cult. That's a band. Anyhow, but there you go. That would be acceptable with me. Okay, and I will not ask the mechanism. Now, if you're wondering, okay, well, at the end, once I do my coupling, I have to remove that protecting group. You're absolutely right. If you're wondering, well, how would I do it? Well, in that case, use trifluoroacetic acid. And the acronym that we use for that is TFA, right? You guys all know what CH3, right? This is acetic acid. So if I replace the 3 hydrogens on the methyl group with 3 fluorines, then I get TFA, trifluoroacetic acid. And it's a much stronger acid than acetic acid because of what? Inductive effects, right? The electron withdrawing ability of the fluorines. And so you can write the condensed formula like this. You can just write above the arrow, you can write TFA. That's totally fine. Either one is totally fine, but that's going to remove the amino group. Now, I'm not going to ask you the mechanism of the deprotection of the BOC group with TFA. However, it is worth noting that if you look at this whole mechanism, I'm going to even write here for you, will not ask. What's cool about it is that you make isobutylene in the process, which is a gas, and CO2, which is a gas. So if you end up forming isobutylene, which is a gas, and CO2, which is a gas, right? That's what the plus or the arrows going up mean. That means this reaction is going to work essentially with 100% yield. So the reaction works very, very well, okay? You could get a 10-year-old to come into the lab and tell them, deprotect this BOC group. All you have to do is put in drops of TFA, and that's going to remove your protecting group. So no big deal there. Now, again, will not ask the deprotection mechanism. Now, you can imagine something I've told you several times this semester is a good organic chemist, she or he will usually have more than one way of doing the same transformation. So besides protecting your amino group as a BOC group, you can also protect it as what we call an FMOC group. And FMOC comes from this 9-fluorenyl methylchloroformate. So this is what you start with as your reagent. So we just call this we call it FMOC chloride, okay? So it's a benzoyl chloride, sorry, a chloroformate, my mistake. Anyhow, it's a chloroformate. You do the reaction here. There's no mechanism provided. Okay, I don't think it's put in here, so don't worry about it. I'll leave them right here for you. Will not ask will not ask this mechanism, but it's very similar to that with the Bach protecting group. And instead of writing out this whole giant ring here, you could also just write, I have my carboxyl group, my no, that's not right. My R group, okay, your nitrogen, and then you can just write F mock. That will be totally acceptable, okay? So as far as removing the F mock group, the way you do it is you use this molecule here. So you take a cyclohexane and you stick a nitrogen in it, and this is called piperidine. Okay, so you use piperidine, and then it ends up making this aromatic anion, kind of like the cyclopentadienyl anion, and then it does this elimination, but you end up eliminating carbon dioxide in the end, and so it drives the reaction to completion, right? Anytime you make a gas in a product, that's a good thing. It's going to push the reaction forward. So now we have protection with Bach, which uses Bach anhydride or diterbutyl dicarbonate. We have protection with MOC, an FMOC, which uses FMOC chloride. Deprotection of the Bach uses TFA or trifluoroacetic acid, and deprotection of the FMOC group uses piperidine. Piperidine, which is this molecule here. Okay, so piperidine, and I drew the structure up there. All right. So what about protection for the carboxyl group? Okay, if we want to protect the carboxyl group, the way we're going to do that, I get some good news, is a reaction that we covered way back in chapter 20. Okay, back in chapter 20, we talked about the synthesis of an ester by using a catalytic amount of acid and water, an alcohol, and removing water along the way, and that produces an ester. Okay, so what are some popular types of esters to make? When it says R here, R, if it's a methyl group, those are great. If it's a benzyl group, so if you're not sure what a benzyl ester is, when R is equal to Bn, that's benzyl, and benzyl is equal to this CH2PH, okay? So either one of those is a really good ester to have. And the reason why benzyl esters are, if you're like, why would you use this specific benzyl ester? Like, what's so great about that? The cool thing about benzyl esters, okay, there's one shown here, is that they can be removed with hydrogenation. So you just put a balloon of hydrogen on top of it, and it pops the benzyl group off, okay? You can also use a mixture of HBr and acetic acid, but I've done it enough to know that using hydrogen gas is much more preferable if you can get it to work, okay? So how do you form the ester? Just ester formation, so catalytic amount of acid, the appropriate alcohol. How do you remove the ester? Well, if it's just a methyl group, that could just be removed by saponification, just using sodium hydroxide. But with the benzyl ester, again, you can use hydrogenolysis, so meaning hydrogenation, or you can treat it with HBr and acetic acid. All right, there you go. So now let's go back to, I don't know, maybe like 10 slides ago or something. We were talking about making a specific peptide. If you wanted to make this very specific peptide, okay, you want to have, let me get a finer tip pen here. You want to have N-C-carbonyl, N-C-carbonyl, okay? So you want to have alanine first, okay? Yeah, so you want to have alanine first, there you go, and glycine second. So you want to make this very specific molecule. Well, that means you have to react the carboxyl group of alanine with the amino group of glycine. So you've got to protect the amino group of alanine. So you're going to treat alanine with Bach anhydride or diterbutyl dicarbonate, okay? You put on the Bach group. So instead of drawing the whole structure out, isn't it great being a peptide chemist? All you have to do is write Bach ALA, okay? You would have to produce an ester or make an ester on glycine. So in this case, they made a methyl ester. So they used just catalytic amount of acid and methanol. So now you write glycine. Notice that the protecting group is on the right-hand side because that's where the C terminus is. Notice this protecting group is on the left-hand side because that's where the N terminus is. Now we do the coupling between this end and this end, okay? So now we put them together like this. And then in step one, we remove the Bach. And then in this one, you remove the methyl ester. Okay, you remove the methyl ester, and then you end up with your dipeptide. Seems like a lot of work, but I'll just tell you the good news, you guys. is that if you're thinking about being a peptide chemist, you don't have to do all of these reactions. You can almost always buy this from a chemical supplier and this from a chemical supplier. So all you have to do is do the coupling and then the deprotection, okay, which works really, really well. So, if you have enough money to buy the starting materials, it can minimize a bit of the work that you have to do. There you go. Now, this is a really cool way of making a dipeptide. Nobody would argue with this. People do it every day to make peptides and tripeptides. They do this all the time. I've done it many, many times in my life, but I've never made like, I don't know, a decapeptide or something. It's never been anything I've ever had to do. But let's say you wanted to make a huge peptide. I don't know, let's say you had like 50 amino acid residues and you wanted to put them together. Doing this method and then protection and deprotection and protection and deprotection, it theoretically it would work, but you guys have maybe done some work in the lab and like actually being in the lab, and you know what it's like. You put all these reagents in a flask and then you end up with this tiny little bit of product and you're like, where did it all go? So it's not going to work if you try to make big peptides. Unless the reactions are really high yielding, you're going to end up with nothing in the end. And so Merrifield, came up with a way to do a synthesize, it says here, superior method for reducing the number of steps significantly. And what he did is he actually took the peptide that you're synthesizing, and you tie it or tether it to an insoluble polymer. So, I mean, it's not soluble. It just stays on these little tiny beads. And that's called solid phase synthesis, or solid phase peptide synthesis, SPPS. And like I told you, he won a Nobel Prize for doing this. So it's a big deal, okay, to be able to do the synthesis of these huge peptides. So here's what it looks like. This is your polymer, okay? We're going to do polymers in chapter 27, okay? Chapter 27, we're going to cover polymers in gross and dirty detail. But the idea, I think you guys know that polymers are just a bunch of, a really big molecule, right? A bunch of repeating units linked together. So this polymer, it almost looks like tiny little white plastic spheres, okay? But on the surface of those spheres, he has all these aromatic rings, but then you have these CH2Cl groups. So what do you know? Those are all susceptible to SN2 reactions. So if we buy the Bloch-protected amino acid, what's going to happen is the carboxylate is going to attack here. We're going to do an SN2, okay? And now you've taken the amino acid, or your first amino acid, and you're going to tether it, right? You're going to tie it into the insoluble beads here, the insoluble polymer, okay? So that's reaction one. And notice your reaction is taking place at a carboxyl group. So when you do the Merrifield synthesis, when you build your peptide, you're starting here. Start here at C terminus, okay? And then you build 1, 2, 3, 4, 5, 6, 7, so on and so forth until you get to the end, okay? So you start with a C terminus and then you build down from there. So once you have it tethered here, it's insoluble, it's not coming off. So now you can see that what you got to do is you got to deprotect this. So you're going to take that Bloch group and you're going to treat it with TFA, and then you can do a DCC coupling. Take a look. You're going to deprotect with TFA, and then you just do a DCC coupling, and then you do it over and over and over and over, and keep adding and adding and adding and adding and adding and adding amino acids, and they don't come off, okay? They just keep getting coupled onto the chain. So then if you're wondering, well, how do I get it off of the chain at the end? How do I get rid of it? The very last step is to treat everything with hydrofluoric acid, okay? Take some hydrofluoric acid, which is a very dangerous acid, but that's going to break this bond right here. So if I underline the HF is going to break it right here, okay? It's going to cut it off of the polymer, and then you're going to release your peptide like that. So it says here, the advantage of solid phase peptide synthesis is the ease of purification, because the polymer beads, again, they're like little tiny white plastic balls. When you put them in solution, they're collected by filtration. You don't have to do any extraction or anything like that. So you just collect them by filtration, put them in the next reaction, and keep going. That's it. Just keep dropping them in and keep going and going and going. And now they have automated ways of doing this. And so it puts in the amino acids in solution. It puts the DCC. It puts the TFA. It just keeps putting everything in. And then in the end, you collect your peptide. So it's pretty remarkable. And again, Merrifield is a pretty big hero. You know, it's a long time ago now, 40 years ago. But yeah, he won the Nobel Prize for this. So a very, very big deal. Anyhow, so this question here, I don't know if I have enough room to squeeze the whole dang thing on here, but it says, outline how you would synthesize this tetrapeptide using the Merrifield synthesis. So we've got phenylalanine, leucine, valine, phenylalanine. So I'm going to switch over to a blank document just so I don't run out of space. So just bear with me here. Okay, this has some of our work from a previous thing here, so I'll just delete all this. Just give me 2 shakes of a lamb's tail here. So today. All right, just make sure I have enough room. There's our Sandmeyer reactions. Those are near and dear to our heart. Okay, so this is question, but the bottom line is this is Merrifield synthesis. Okay, this is what we're talking about here. And the tetrapeptide that we want to make, what was it? It was phenylalanine, leucine, valine, and then phenylalanine. Okay, so we want to make this guy by the Merrifield synthesis. So what we're going to do is we're going to start here, and then we're going to end here. Okay, so we start at the C terminus, if you will, or we start on the right-hand side, and then we work our way left. Okay, so here's what you would do, is you would start with the carboxylate of the phenylalanine. So I'm just going to write that down here. And if I write the carboxylate, again, this is just the conjugate base here, of the phenylalanine, you're going to have the Bach protecting group on the nitrogen, always, okay? So this is, again, this is your phenylalanine, your first one, okay? I'm going to delete that just so I don't have too much on there. So then first, if you're like, well, how do I draw the whole dang polymer? Good question. All you do is this, is you put the CH2, Cl, and then just write a circle. And then usually we shade that in and we say that is the polymer, okay? Or sometimes people will actually write polymer in there. I don't like that. I just like shading it in, okay? Just shade it in like that and say that is the polymer, okay? So it's going to do the SN2 like this, and then it's going to be appended onto the polymer. So what's that going to look like? Now I'm going to flip it a little bit. I'm going to rotate this bond, and you'll see why in just a second. It actually makes it easier to understand. So I'm going to put my Bach and H. I'm going to put my R group down here, and then here's my bond to my polymer, like that. Okay, so now I've got the first group stuck to the polymer. So now, in order to put the valine on there, the first step, step 1, is going to be to treat this with TFA. Once you treat it with TFA, what it's going to do is it's going to knock all this off, and you're going to end up with NH2. Okay, now I'm going to put it back the way it was because you guys are just going to assume that. So we knock the Bach group off. Now we have the free amine, and it's free to couple with the valine. So we're going to put in the valine residue. So I'm going to write it the same way. So Bach and H. Okay, here's my carboxyl group. Don't worry about the stereochemistry. Let's just get the carbon atoms in there. So there's my valine, and I'm going to need dicyclohexyl carbodiamide. Okay, so now it's going to get a little bit bigger. So what we're going to do is this, to make it easier to draw, is we're going to start with the polymer. Okay, so there's my polymer, there's my methylene. Now, instead of writing this whole thing out, I'm going to say phenylalanine. So I'm going to put a circle like this, and I'm going to put PHE. Then I'm going to have it linked to my valine, so I'll just write VAL. And the valine is Bach protected, so I'm going to put NH Bach, just so everybody knows there's still a Bach group on that valine. Okay? So now, instead of drawing out the structure of everything, you see that we can actually simplify it a little bit if we just use some condensed structure. So what's the next step going to be? The next step is going to be first to treat it with TFA to knock off the Bach group, and then we're going to put on the Bach protected leucine. So we put in our Bach protected leucine, which is going to look like this. So I'll just draw the whole thing out here. Bach, NH. And then we have, and remember, a leucine, we've seen it quite a few times today. It's got an isobutyl group in it, like that. So that's our leucine. So we'll put here LEU. This is our VAL. This was our phenylalanine. Maybe I should have left that there to begin with. So now, to draw the intermediate, we have our polymer, CH2. Then we've got 1, 2, 3 amino acid residues. So we have phenylalanine, valine, leucine, and then we have NH Bach, like that. Okay, got to keep going. So next step is going to be to hit it with what? TF. Step 1, TFA. Step 2 is going to be another phenylalanine. So let's put in our phenylalanine here, which is going to look something like this. We'll put Bach and come on, iPad. NH, like this. There we go. There's our carboxyl group. Then we'll put our CH2, and I'll just put pH for our phenyl, like this. Okay, so now we're going to have, and I just use the copy paste tool. There's a lot of circles to draw here, so I'll just copy this, paste it down here, and now we've got our polymer, and we have all 4 amino acid residues on there. So we'll put phenylalanine, and then we have NH. I'm running out of space here, Bach. And then to liberate everything, we're going to need TFA to knock off the Bach. So we're going to do step 1, TFA. Step 2, HF to knock it off the polymer. And then we have the part that we need, which is this part here. So we'll just copy that and move it over here. And there is our beautiful tetrapeptide, just like that. All right, so Merrifield, remember, you're going to start on the right-hand side. See if I can squeeze all that in here. But that is the Merrifield synthesis. Pretty brilliant synthesis. You got to hand it to Merrifield. It's a pretty bright guy to put all that chemistry together. So moving forward, okay, that covers all of the chapter. Now, I know that a lot of you have studied advanced biology. Not all, but I know that many of you have. So if you want to get ahead for biochemistry in the fall, or whenever you're going to take it, you might want to look at the protein structure. So primary structure, so if I just describe it to you very quickly, this is just the structure of insulin here. You can see it's made out of 2 chains. It's got an intrastrand disulfide bridge, and it's got 2 interstrand disulfide bridges in insulin here. But primary structure is nothing more than the amide bonds. It's just the order that the amino acids come in, okay? So first you have a glycine, the isoleucine, right? Then a valine, then a glutamic acid, so on and so forth, right? That's primary structure. Secondary structure, there's 2 types of secondary structure. There's something called an alpha helix, and there's another one called a beta pleated sheet. And those are covered here. So the alpha helix, you guys have probably all studied the double helix in DNA, which is held together by hydrogen bonding. Well, the helix in the alpha helix, which is a single strand, is held together by hydrogen bonds that are in between the amino acid residues. And then a beta pleated sheet, if you've ever looked sideways at corrugated cardboard, how it has like the ripples in it like this, in corrugated cardboard, or maybe drapes or something like that. That's kind of what a beta pleated sheet looks like. Now, beyond secondary, and then I guess in biochemistry, you'll talk about parallel and anti-parallel beta pleated sheets. So it shows some secondary structure here with this ribbon diagram. Tertiary structure is that when you have a chain of amino acids linked together, they're going to fold in on themselves and produce some kind of 3-dimensional structure. And that's what tertiary structure is. And so in biochemistry, we'll talk about how the non-polar R groups are going to go inside in an aqueous environment so that they can, experience van der Waals attractions and things like that. Whereas polar groups tend to be on the exterior so that they can participate in salt bridges and hydrogen bonding. Then you'll also talk about something like denaturation. Denaturation, if you've ever taken your hand and by mistake, if you've by accident put your hand in the oven to grab a cookie sheet, let's say, and you touched the hot metal in the oven and you noticed your skin gets burnt there immediately and it changes color, that's the proteins in your skin being denatured, because the intermolecular forces that hold the proteins tertiary structure together is not covalent bonds, okay? It's all intermolecular forces, and those can be broken. And it's not just temperature that can do it. If you've ever added acid like vinegar to milk, you'll see that the protein there will start to precipitate. What else? Quaternary structure is when you have two or more amino acids with tertiary structure coming together. So hemoglobin is a great example of that. It's got two alpha subunits, two beta subunits that you can read about. Also protein, structural proteins like fibrous proteins like keratin and things like that. If you want to take the time to read up on those, that might be useful to look at fibrous proteins. And then enzymes, right? I mean, if you go back to General Chemistry 1, you learn about how enzymes lower activation energies. Well, and we talked about catalysts. Well, an enzyme is nothing more than a biological catalyst. And an enzyme is nothing more than a protein. Okay, it's just a protein that has a specific function. And so trypsin, chymotrypsin, these were examples of enzymes that we took a look at. Transport proteins, you'll talk about those. You talk about hemoglobin and how it has the heme subunit inside. This molecule here is called heme, and it's a prosthetic group because it's part of the protein, but it's not made out of amino acids. But you can see how heme here has the iron bound in the middle, and it's what allows oxygen to bind to hemoglobin. Anyhow, you'll discuss that in biochemistry. So again, sections 25.7 and 25.8, I'll leave that as an FYI.